Okay, hello everyone and welcome back to another session of Automata on Infinite Words. So let me start by just overviewing what we learned in the previous session. So in the previous session, we defined automata on infinite words. Especially we said that we mostly focus on parity automata and Buki automata, and we said that there are differences between deterministic and non-deterministic. We also say that language L is omega regular if there is a non-deterministic Buki automaton that accepts exactly that language. So if L is the language of a non-deterministic Buki automaton, then we call it omega regular. And then we also talked about properties of closure of these languages under different set operations. We showed that the languages that are realized by deterministic Buki automata are closed under union and intersection. Well, the intersection part was actually your homework, so I guess you already know how to solve that. But we also showed that they are not closed under complementation. And the example that we gave for this was basically the language that accepts any string that has infinitely many zeros. So we have a deterministic Buki automaton that accepts any string that has infinitely many zeros. But if you take the complement, the language of strings that have only finitely many zeros, then there is no deterministic Buki automaton for them. So this showed us that non-deterministic Buki automata are strictly more expressive than deterministic Buki automata. Well, this is because anything you can do with a DBW, you can definitely do with an NBW, because, well, DBW is a special case of MBW. You just don't use the non-determinism. And also we had, again, this example of the language of strings that have finitely many zeros. And we showed that there is an NBW for this, but there's no DBW. So NBWs are strictly more expressive. And we also showed that the languages of NBWs, or what we call omega regular languages, are closed under union and intersection. But we didn't quite cover complementation in the previous session, and this is what we will do either in this session or the next session based on how fast we can go. Okay. So moving on, what are some classical problems that we should consider when thinking about automata? So if you think about your undergraduate courses on formal languages and automata, you probably have seen some of these examples before. But I'm just going to go through the classical problems that we will look at. So one of the most classical problems is emptiness. So you're given an automaton as input. And for now, let's say that we are only talking about Buki automata, but we have both deterministic variant and non-deterministic variant. So the emptiness problem is that you are given an automaton as input, and the question is whether the language of the automaton is empty. So whether the automaton rejects everything. Then we have kind of a dual to this, which is universality. In universality, the problem is that you are given an automata, and the question is whether the language consists of all infinite strings. So remember that sigma was our alphabet, and sigma to the power of omega would be all the infinite strings that we have. So what universality asks is that given an automaton A, does it accept everything? Then, of course, we have complementation, which was another thing that we saw a little bit in the previous session. And the idea is that you are given a Buki automaton A, which can be deterministic or non-deterministic. And you want to find a non-deterministic Buki automaton B such that the language of B is the complement of the language of A. Okay. And we actually saw one case of this in the previous session. So we saw how you can complement a deterministic Buki automaton and get a non-deterministic Buki automaton. Not that we cannot get deterministic here because, well, it's not closed under complementation. But really, the more involved case is what happens when you have a non-deterministic Buki automaton and you want to also find another non-deterministic Buki automaton that complements it. So this is a problem that we will spend a lot of time on. And actually, if you look at universality, universality is kind of a combination of complementation and emptiness. So if I want to see whether some automaton A is universal, I can first complement it, get the automaton B, and check whether B is empty, right? So universality can be seen as a combination of emptiness and complementation. And another problem that we look into is containment. So the idea of containment is that you have two different automata A and B, and you want to figure out whether the language of A is a subset of the language of B. And again, if you look at it with a little more detail, you will see that containment is also kind of a special case of the previous one. So if I want to decide this, what I can do is that I can just take the complement of B and then take its intersection with A and then do emptiness checking. And if that automaton is empty, then I know that the language of A is a subset of the language of B. So containment is basically complementation, intersection, and emptiness. And we are mostly going to talk about the first three problems. The problem that actually has most of the use cases is containment, but as I just said, it's just a combination of the previous ones. So we can just focus on the ones that are easier in a sense. And they're easier because they are focusing on one automaton instead of two. Okay, so let's start with emptiness. So let's say that I've given you some automaton A. It's a Buki automaton. It can be deterministic or non-deterministic, and it has n states. And what I want you to do is tell me whether the language of A is empty. Well, let's just do some definition chasing and see what it means for the language of A to be empty. So, or maybe we can just look at the dual and see what it means for the language of A to be non-empty. If the language of A is non-empty, then that means that there is some word W that is accepted by A, right? And this, well, because we are working on infinite automata, this is infinite for W. And well, if W is accepted, then it means that there is an accepting run over W. And this is true for both deterministic and non-deterministic, because, well, in the deterministic case, there is only one run, so there exists an accepting run, and in the non-deterministic case, this was basically the definition. Okay, so the problem that we want to solve is equivalent to deciding whether A has an accepting run. Okay, so let's say this is my automaton A, and let's say that T is the set of accepting states in A. What was the definition of an accepting run? A run was accepting if it visited T infinitely many times, right? Infinitely often. So we have to decide whether there is a path in the underlying graph that starts from some initial vertex and visits T infinitely many times, right? And now we don't care about the input string at all. As long as there is a path that visits T infinitely many times, we can generate a string for it. Okay, so in a sense, I can now think of this underlying graph as a Buki game, but it's a single player Buki game in the sense that all of the vertices belong to player one. So I have one player that just wants to find the path that visits all the, that visits the accepting states infinitely many times. So this is a special case of a Buki game. And we have already seen that this is solvable in polynomial time. So we had the classical algorithm for Buki, which took order nm. And we also had the hierarchical decomposition algorithm, which took order n squared. But can we do better? And the answer is actually yes, because this is a very simple game, right? It's a game where only player one vertices exist. There is nothing for player two to do. So if we consider this whole thing as just a graph, we can look at the strongly connected components of this graph, okay? And if I can start from one of my starting vertices and then get to one of the strongly connected components that contains one of my target vertices, then I can just stay in that strongly connected component forever, right? But well, this of course does not apply to trivial components with one vertex. So it has to have at least two vertices, because otherwise I can't stay in the strongly connected component. But anyway, so if I have a strongly connected component, or maybe instead of saying that it should have two vertices, let me just say if it's not transitional in the sense that we can visit it many times. There's a strongly connected component instead of with at least two vertices, because we can also have a strongly connected component that is just one vertex but has an edge to itself. So if there is non-transitional strongly connected component, and by that I mean any strongly connected component in which we can stay. It's not just one vertex and an outgoing edge. Okay. If I can get to such a strongly connected component, and if that strongly connected component has one of my accepting states, then well, I can just loop around in there, cycle around, and see this accepting state infinitely many times. And actually, you can prove the other way around as well. So if there is an infinite path that is accepting, it has to visit one of the accepting states infinitely many times. So it starts from one of the initial vertices and goes into the connected component, into the strongly connected component of an accepting state, and then visits it infinitely many times. So this is if and only if, and this algorithm actually works. So what do we need to do for this algorithm? We basically just need to compute strongly connected components of our graph, and then do a simple DFS on the strongly connected components. And well, I guess you should have had this in basic algorithms courses. You can compute strongly connected components in linear time. And this is also actually done by a depth-first search by DFS. So we can actually decide emptiness for Buki automata in linear time. And note that this applied to both deterministic and non-deterministic Buki automata. So emptiness is a very easy problem. Okay, now the thing is that many people assume that because emptiness is easy and because universality is kind of like emptiness of the complement, then universality should also be easy. But now I'm going to show you that this is not the case. And actually this is not the case because computing the complement is hard. But before doing that, I'm just going to talk about universality itself. So let's first take the easy case again, the case of deterministic Buki automaton, and let's say that I have a deterministic Buki automaton A, it has n states, and I want to decide whether it's universal. I want to decide whether the language of A is all infinite strings, whether L accepts everything. Oh, sorry, whether A accepts everything. Okay. So we can do that definition chasing that we did before again. So if A accepts everything, if the language is everything, then every infinite word is accepted. That means that every run of A is accepting. Note that because A is a deterministic Buki automaton, then every infinite word has a unique run, and every run has a unique infinite word, right? So when I say that every word is accepted, it means that every run is accepting. And again, let's just look at the definition. If T is the set of accepting states in my automaton A, a run is accepting if it visits T infinitely often, right? So how can we formulate this in terms of the underlying graph of the automaton? Well, we can say that in the underlying graph, we want to see if there is a path. We want to see if every infinite path visits T infinitely many times, okay? And this is equivalent to deciding whether there is a path, there is an infinite path that visits T only finitely many times. Because if there is such a path, then we know that the answer to universality is no, and otherwise the answer is yes. Okay, so what I want to decide is whether there is an infinite path that visits T only finitely many times. Again, I can look at this as a two-player game on graph, and this is a single-player Ko-Buki game. Because all vertices, we can say, belong to player one. And player one wants to visit target vertices finitely many times. So this is a Kobuki objective. And again, it can be solved in order nm or order n squared. And of course, we can do it in linear time as well. So again, here instead of has more than one vertex, let me say it's non-transitional. So if every strongly connected component that is reachable from some initial vertex and is non-transitional also has a target in it. Sorry, the exact opposite. Right. No. Okay. So I'm talking about universality here. Here I was talking about non-universality, and this is now again universality. So my automaton is universal if for every strongly connected component that can last forever in my runs, so every strongly connected component that is non-transitional and is reachable from an initial vertex, I have at least one target vertex in it. So this ensures that every path that I take would go basically to one of these non-transitional strongly connected components and just cycle in there. So it has to see, actually not really. Well, basically there is a bad case, and the bad case is if you have, okay, this is wrong because the bad case is that you can have a strongly connected component that actually includes a target vertex, but then you have a cycle in this strongly connected component that does not include the target vertex. So I can't just say it in terms of strongly connected components. I don't know what I was thinking here. What I can say here is that if every reachable cycle contains a target vertex, so if every cycle that can be reached starting from one of the initial vertices has a target vertex in it, then you can be sure that no matter how you walk on this graph, every infinite walk will repeat some cycle infinitely many times. And then because every cycle has a target vertex, the whole automaton becomes universal. Okay. Now, the important question here is that does this kind of algorithm extend to the non-deterministic case? So suppose that instead of having a deterministic Poky automaton, I had a non-deterministic Poky automaton, and I just tried the exact same thing. What goes wrong? Does it actually work, or is something broken if I do this on non-deterministic Poky automaton? So let's start from the top and see what happens if we have non-determinism. So this part is fine and it goes through. But then the next part says that every run is accepting. This is the thing that breaks when we go to non-deterministic Poky automaton. So basically you can have a non-deterministic Poky automaton that has some non-accepting runs, but at the same time, for every word, it has at least one accepting run, right? So your non-deterministic Poky automaton can be universal without actually having all of its runs be accepting, right? So this is the part that does not extend. And actually, this is enough for the problem to become much harder. And now I'm going to show you why. So let's talk about universality of non-deterministic Boole automata. So let's just review the problem. We have a Boole automaton that has non-determinism. It's called A. It has n states. And we want to see whether it accepts everything. Okay? Or we can just take the negation and say that we want to see whether there is some string that is not accepted, right? So that would be non-universality. And what I claim is that non-universality of non-deterministic Boole automaton is NP-hard. Okay? And note that I'm not really claiming that the problem is in NP. All I'm claiming is that it's NP-hard. So it's harder than every other problem in NP. Okay. So before proving this claim, let's see what it means for complementation. So let's say that you believe me that this claim is true. I think a corollary of this claim is that we cannot hope for any polynomial time complementation procedure for non-deterministic Boole automata. Can you say why? So why is it that if non-universality is NP-hard, then we have no hope for p-time complementation? Okay, so what does it mean when we say a problem is NP-hard? If we want to do a very hand-wavy, yes, the thing in the chat is correct. So if we want to do a very hand-wavy kind of thing, because we don't know whether P is equal to NP, and because most computer scientists believe that it's not likely that we can find a polynomial time algorithm for non-universality, right? So that means that it's also unlikely that we can find a polynomial time algorithm for universality, right? Because universality is just a negation of non-universality. Okay, but if we somehow have a polynomial time algorithm for complementation, I can just take my non-deterministic Boole automaton A and then complement it using this polynomial time algorithm, and then just check emptiness, which I showed can be done in linear time, right? And this will answer universality of my original automata. So because this problem is hard, this is also hard. And you cannot hope for any p-time complementation. Okay. Now let's go back to the claim and try to prove it. I want to prove that non-universality of non-deterministic Boole automaton is NP-hard. So let's just be a little bit more concrete about what this means. This means that my input is a non-deterministic Boole automaton, and my output should be 1 if there is some string that is not accepted by this non-deterministic Boole automaton, and it should be 0 if every string is accepted. So that's why I'm calling it non-universality instead of universality. It's just the opposite of universality. Okay. And so from your basic algorithms or complexity courses, you would know how we can prove NP-hardness. Basically, if you want to prove NP-hardness, one of the most classical ways of doing it is to find a reduction from another NP-hard problem. We can use any problem, but the problem that I actually like for this reduction is tree coloring. And tree coloring is, I think, one of the 21 CARP problems. It's a classic NP-complete problem. So let's just see what tree coloring is. So actually, the name says all of it. You have a graph consisting of a set of vertices and a set of edges. And this is an undirected graph. And the question is it possible to color the vertices with 3 colors, for example, red, green, and blue, such that no 2 adjacent vertices have the same color? So this is the tree coloring problem. And we know that it's NP complete. Okay, before continuing, I can just say that without lots of generality, we can assume that this graph G is connected, right? Because if my graph is not connected, I can just find 3 colorings for each one of its connected components. So let's say that given a connected graph G, is it possible to color the vertices in G with 3 colors such that no 2 adjacent vertices have the same color? Okay. Now, what do I want to do? I want to reduce this problem to non-universality of non-deterministic Bucchi automata. So I am given a graph G, and what I want to do is that I want to create some non-deterministic Bucchi automaton such that this graph is 3 colorable if and only if that automaton is non-universal. Okay. So the way I do this is actually in several steps. I create a lot of different automata, and then at the end I will take their union. Let me say that all of the automata that I use will have the same alphabet. So my alphabet is basically my set of vertices times the set of colors, the 3 colors that I had RGB. So every infinite word is basically an infinite sequence of pairs of the form VC, where V is a vertex and C is one of the 3 colors. Right? So the inputs to my automata are infinite sequences of these pairs. And all of the non-deterministic Bucchi automata that I define use this same alphabet. Okay. So let's see what kind of automata we can define. And at first, you might not really see the intuition behind this, but then at the very end, you will see why these automata are actually useful. Okay. So first of all, let's say this is my graph, and let's say that I've numbered the vertices. The first automaton that I create, and which I call it A, basically accepts all the words that are not valid paths in the original graph. And this automaton A ignores all the colors, right? So, for example, if the input sequence is this, so the input sequence is 4 red, 3 red, 2 green, and then this part just repeats forever, 1 blue, 6 blue, right? So would this be accepted by the automaton A? So let's see if this is a valid path in the graph. So if I start from 4 and go to 3, then 2, then 1, then 6, then again 1, 6, 1, 6, 1, 6, so on. So this is a valid path in my graph, right? And not that I'm ignoring all the colors in the sequence, I'm just looking at the vertices. So because this is a valid path in the graph, this is going to be rejected by my automaton A, because the automaton A accepts all paths that are not valid in G. Okay, but on the other hand, if I have a sequence that starts with 4 red, 8 green, because there is no edge from 4 to 8, then this is an invalid path. So it is accepted by A, because A accepts all the invalid paths. And again, I cannot stress this enough. A ignores all of the colors. So we don't care about these colors here at all. Okay, so how can we actually create such an automaton? It's not too hard. So sigma is, well, just these pairs, that's fine. So the set of states in my automaton would be the set of vertices, but I also add 2 new states. So I call one of these Q0, which is my initial state. And the other one is just the bottom state. And well, my automaton starts from Q0. And my goal is to see the bottom state infinitely many times. Okay, and now the transitions. How do I do transitions? Well, the transitions basically follow the path on the graph. So if I start from the starting vertex Q0 and the first letter that I see is vertex V and color C, I just go to vertex V. if I start at a vertex and I see vertex V color C, I also go to that vertex V, assuming that there is an edge that I can go to. But if there is no edge in the original graph, I just go to bottom, right? So whenever I go through something that is not a valid path in my original graph, in the automaton, I will reach this bottom state. And then I just define that when I'm in the bottom, I will always stay there, right? And note that my set of target states was just the bottom. So the goal is to just reach this bottom state. And we reach this bottom state only when our path is not valid in G. Only when we take some, we go from some vertex U to some vertex V, but that edge does not exist in the graph, right? So this automaton A accepts an infinite string if and only if, when we ignore its colors, the thing that remains is not a valid path in G. Okay, any questions until here? Okay, great, so we can move on. Here's the second automaton that I want to define. I call this one B. And the thing about B is that it ignores the graph entirely. So if you look at A, it didn't ignore the graph. It cared about when we have edges. So A was dependent on the graph itself. But this automaton B that I'm going to create ignores the graph entirely. And basically, it accepts all words in which there is a vertex that appears with two different colors. Okay? So, for example, consider this word. So first, we have vertex 1 with color red, then vertex 3 with color blue, vertex 4 with color green, 1 with color red, 7 with color blue. And if you look at these, no vertex appears with more than one color, right? So this will be rejected because we need to have at least one vertex that appears with two different colors. But this string here, well, here we have one with color red, and then we have one with color blue. So this will be accepted by B. Now, how can we create this automaton B? Well, this is also quite easy. So what do we want to see? We want to see cases where we had some vertex, for example, 1 appear with some color red, and then after a while, we want the same vertex to appear with another color, right? So this is what this automaton does. We start here at Q0, we ignore some prefix, then at some point we see 1R, and then we can ignore, and then we can see 1 with another color and then accept. This is a trap that accepts. And I can just add many different branches for all of the combinations. So if I see 1 red first and then see 1 blue, or if I see 1 red and 1 green, right? Or if I see 1 blue and then 1 red and so on. And for every color and every vertex, I can basically create this huge thing that has n times 3 different, well, not actually. So yeah, it has n times 6 different branches. So for every vertex, I have 6 different branches, which are the different combinations of colors that I can see. So overall, it's n times 6 branches. So are you convinced that this does the right thing? That this automaton B accepts all words in which a vertex appears with at least 2 different colors? Okay, great. So let's go to our next automaton. So the third automaton that I want to create, which is called C, accepts all the words which do not contain all edges of the graph. Now, you're seeing now some sort of a theme here. Basically, the idea is that I'm creating different gadgets, different small automata that accept unwanted paths, right? So here, my automaton C accepts any infinite word that does not contain all edges of the graph. So let's say that I have a single edge, UV. Can I create a non-deterministic Bookey automaton that accepts all the words that do not visit UV? And note that so here we are ignoring colors again. So C ignores colors. Well, if I have an edge UV and I want to have an automaton that makes sure that we will never see UV or VU, it's actually this automaton. So we start at this vertex here. As long as the thing that we are seeing is not U or V, and I'm ignoring the colors, we stay here. As soon as we see U, we go here, and if then we see V, we will go here, which is a trap and gets us rejected. And this is, again, the exact same thing. So if I see V and then see U, again, I'm in a trap, right? And as soon as I see something else other than U or V, I just go back to the initial state. So this automaton accepts all the strings that do not have UV or VU in them, ignoring the colors, right? But what did we want for C? We wanted it to accept all words that do not contain any of the edges, not just the edge UV. So we can just create this gadget for each one of our edges. So for each one of our edges, I create one of these automata, and then we can just take the union of all of them. Right? So taking the union of all of them gives us an automaton that accepts a word if and only if there is at least one edge of the graph that does not appear in that word. And this is exactly what we want for C. Okay. Bear with me, there is one more. Okay. Finally, we have an automaton that ignores the vertices and only looks at the colors in the sequence. And this is our fourth automaton, D. It accepts all words that have the same color twice in a row. So for example, it accepts this word because this one is red and the next one is also red. But it rejects this word because we have red, blue, red, blue, red, blue. Okay. Now, and this one completely ignores the vertices, only looks at the colors. So how can we create this kind of automaton? Again, this is very simple, especially because we have non-determinism. We can say that, well, we just ignore some prefix. And then if at some point we can read two different letters that are both red, we will go here and accept. If we can read two letters that are both green, we will go here and accept. And if we can read two letters that are both blue, we go here and accept. So this automaton accepts all strings in which there are two places where we have the same color just appearing in both. And these two places are right next to each other. So two simultaneous appearances of the same color. Okay, now, so we saw all these graphs, all these automata. And in a sense, the intuition is that if you look at the original graph, each one of these automata is accepting words that do something bad in the original graph, right? So if I want to look at my word as a, let's say that I have my graph and I have a tree coloring of it, right? I can start somewhere in this graph and go through an infinite path, and then I can just write the vertices and the colors that I see in this path, right? Now, what are the bad cases that can happen? I'm basically just accepting all the bad cases in this automaton that I created. So one bad case is that there is no edge. For example, there is no edge from 5 to 3, but I'm going from 5 to 3. This will be accepted by automaton A. Another bad case is that I'm seeing the same vertex, for example, vertex 1, but once I'm seeing it with color red and once I'm seeing it with color blue. If this happens, then This bad case is accepted by automaton B. Another bad case is that there is some edge that I don't see at all. This bad case is accepted by automaton C. Another bad case is that I have two vertices, letters that come right after each other. So I went from one vertex, for example, from vertex 1 to vertex 2 here. And both of these vertices had the same color. So in a tree coloring, we don't want these vertices to have the same color. This bad case is accepted by automaton D. So I can basically just take the union of all these automata and I can call it E. So I define E as the union of A, B, C, and D. And my claim is that E is universal if and only if my original graph G is not three-colorable. Or equivalently, E is non-universal if and only if G is three-colorable. Okay, so what is the proof? The proof is basically what I told you right now. We can make it a little bit more formal. So when does E accept an infinite word? E accepts an infinite word if at least one of the following four cases, which were our bad cases, happen. So one case is that the word is not a valid path on G at all. Another case is that the word does not assign a unique color to each vertex. So it assigns more than one color to a given vertex. Another bad case is that the word does not visit some of the edges of G. So it's ignoring part of the graph. And the final bad case is that the word has two steps, two simultaneous steps that have the same color. Now, if G is three-colorable and phi is a valid three-coloring, for example, as in here. So this is the Peterson graph and a three-coloring. Then what can I do? Well, remember that I assumed that my graph is connected. So I have a connected graph and I have a valid three-coloring. So I can start anywhere in this graph and just go on an infinite path. And the only thing that I have to make sure is that I visit all of the edges of the graph. And as I go through this path, I don't just write the number of vertices, I also write their colors. Right? And this gives me an infinite word. And this infinite word will be rejected by the automaton E. Why? Because in this infinite word, well, first of all, it's a valid path on G. This is by construction. It definitely assigns a unique color to each vertex, again, because we had this coloring phi. And it visits all edges of G, and this was also by construction. I said I take an infinite path that visits all the edges. And why can I do this? Because the graph is connected. And finally, because this was a valid tree coloring, every time that I'm seeing two vertices right after each other, they have different colors. So it doesn't satisfy any of these conditions and it gets rejected by E. So what I proved here is that if my graph is tree colorable, then my non-deterministic Buki automaton E is non-universal. Now I want to prove the other side, and the other side is very much the same, right? So if I have an infinite word that is not accepted by E, what does this mean? This means that I have an infinite sequence of vertices and colors of my graph such that none of these hold. So this infinite sequence is a valid path on my graph. And it also assigns a unique color to every vertex. And it also visits all of the edges of my graph. So it's really assigning a color to each one of the vertices. And it's also visiting every edge. And any two simultaneous steps have different colors. So it means that, well, because I'm visiting every edge, the two vertices at the two sides of my edge have different colors. So basically, any infinite word that is not accepted by E just gives me the coloring that I need for my graph, right? And this ends the reduction. So basically what we proved is that non-universality of non-deterministic Buki automaton is NP-hard. Okay, any questions? So this session is probably going to be the most mathematical session that we have. But you don't really need to remember all these proofs. All I want you to know is that universality is hard, complementation is hard, but emptiness is easy. That's basically all I want you to know. Okay. So what's next? So the next thing that we can talk about is actually the one thing that we've been avoiding for so long, and it's complementation. So let's see how we can do complementation of non-deterministic Poky automata. And remember that we actually had in the previous session complementation of deterministic Poky automata. So let me just open that one again. So the first question is, why doesn't the same procedure work for non-deterministic? Okay. So this was the special case that we saw at the end of the previous session. We had a deterministic Poky automaton, and we wanted to complement this deterministic Poky automaton and get a non-deterministic Poky automaton. And the idea that we had was very simple. We said, okay, just let's take 2 copies of the original automaton. And in the second copy, let's remove all the original target vertices. And let's say that we continue in the first automaton until at some point we commit to a transition to the second one. And when we transition to the second one, we will no longer see any of the target vertices of the original automaton. So the language of this automaton would be the complement of the language of the original one. Now, so in the last session, one of the things that I asked you is that why can't the complement itself be deterministic? And this was basically due to the fact that we saw that proof that deterministic automata are not closed under complementation, but also because we need the non-determinism because we don't know at what point we want to really commit to going from part 1 to part 2, right? So that was the need that we had for non-determinism. But let's now ask a slightly different problem. What happens if my original automaton was already non-deterministic and I just did this? Why don't I get the complement? Why is this not enough? Well, one simple answer to this would be that we already saw that we cannot have polynomial time algorithms for doing the complement, right? So this shouldn't work. But can you tell me why it doesn't work? Like what goes wrong in this construction? Any ideas? Well, it's because of the non-determinism, basically, right? Because, well, when it was deterministic, for every input word, we had a unique run of the automaton. So I had a unique run here in A, and I just had to figure out when I will commit to going to the second part, right? But when I have a non-deterministic A, I have many different runs already inside of A. And A accepts a string if even one of these runs are accepting. So what I would need for complementing A is that I need to make sure that every run ends up in the second part. It's not enough to say that just one run ends up in the second part. And this is what makes this whole structure not work. Because with this structure, if even one of your runs can go to the second part and then stay there forever, the whole thing accepts. But then on the same word, you might have another run in A that just stays here and also accepts. So this is why this thing does not work with non-determinism. But let's go to the non-deterministic part and let's see what we can do there. Okay, so our problem is, again, that we have a non-deterministic Boole automaton A, and we want to construct another non-deterministic Boole automaton B such that the language of B is the complement of the language of A. And we already know that we cannot really find polynomial time algorithms. But what happens if we don't care about the runtime? So what happens if I just tell you, give me an algorithm, and the only thing that I care about is whether the problem is decidable. I just want this algorithm to terminate and give me an output. I don't care how much time it takes. Can you do that or not? And also another question is, which is currently still unanswered, and we will also answer using this algorithm, is, does such an automaton B even exist? So can we be sure that omega regular languages are closed under complementation or not? Okay. So the construction that I'm going to show you and the algorithm that I'm going to show you was actually first found by Boole himself. And I guess this was a long time ago, maybe 1950s or 60s. And it's a very nice construction. It's not optimal. So the construction that I'm going to show you, actually, its runtime is doubly exponential. And there are exponential constructions as well. So if you want to find those, you can look into the works of Nir Peterman and Jean-François Raskin. But for now, the only thing that I want to answer is whether there is a terminating algorithm that can find this B. And the construction itself is very beautiful, and it needs some Ramsey theory. So let's get into this and see some Ramsey theory. For those of you who have taken a combinatorics or graph theory course, you have probably seen this basic theorem, which says that if we have a graph with 6 different vertices, and if we color each one of vertices with 2 colors, red or blue, then there is definitely a triangle such that, okay, okay. If we have a graph, a complete graph with 6 vertices, and we color each one of the edges with red or blue, then there is definitely a triangle that is monochrome. So there is a triangle that has all of its edges have the same color. And so one way of proving this is to just go through all the colorings, and someone on Wikipedia created this really nice image that goes through all the possible colorings of the edges of a 6-vertex graph and shows that we always have that monochrome triangle. But the way that we usually prove this is using pigeonhole principle. And basically the idea is this: take some vertex, let's call it U. This is vertex U. And there are 5 edges going out of U, right? And we have 2 colors. Because we have 2 colors and 5 edges, by pigeonhole principle, there are 3 of these edges that have the same color. Let's say there are 3 of them that are blue. So let's say this one, and this one are blue. Now we just look at the vertices at the end of these edges. If there is an edge between 2 of these vertices that is also blue, then we already have a triangle, right? That blue edge and also the edges to U. But if all of the edges between these 3 are red, then, well, we have a red triangle between these 3. So in each case, we have a monochrome triangle, a triangle that has the same color for all of its edges. So this is the simplest case of Ramsey numbers. Well, it's the 3-3 case. But what we're really much more interested about is what happens if the graphs are much larger. So you can imagine that, for example, if you want to have a monochrome click of size 4 or 5 or so on, this would be possible if your graph is large enough. But what I'm actually much more interested in, because well, this whole module is about infinite words, is what happens on infinite graphs. And this is what I'm going to show you now. So this is Ramsey theorem for infinite graphs. So let's say that I have an infinite graph, and for the sake of argument, let's say that my vertex set is countable for now. I don't really need the countability, but let's say it is. So I have an infinite set V of vertices, and it's a complete graph. So my set of edges is V times V. Or, well, actually, not exactly V times V, because I'm talking about undirected graphs. So my set of vertices is all pairs of vertices, basically, all subsets of size 2 of V. Okay, so I have a complete graph on an infinite vertex set V. And let's say instead of 2 colors, now I have C colors, but the number of colors is finite. Okay. So I have finitely many colors, but an infinite complete graph. And I have colored every edge by one of these C colors. Now, what I claim is that there is an infinite monochrome clique in G. So there is an infinite subset of vertices such that the edges between these vertices all have the same color. And now I'm going to prove this. The proof is actually very similar to the basic case of Ramsey that we just saw here. It starts by taking one vertex. So I take one vertex and call it A1. And then I say, okay, if you look at my graph, I have finitely many colors, but I have infinitely many neighbors for A1 because this is a complete graph on an infinite vertex set. So there should be some color C1 such that A1 has infinitely many neighbors with that edge color. So there are infinitely many edges of color C1 going out of A1. And let's call the endpoints of these edges V1. So V1 is the set of neighbors of A1 such that the edge between them and A1 was of color C1. And I know that V1 is infinite because this is how I chose C1. Okay. Now, what I say is that forget about the rest of the graph and only look into V1. Let's say I only look into the induced graph on V1. So the vertex set is now V1. And the edge set is, well, it was a complete graph. So I have edges between every 2 vertices. So again, V1 is infinite. So there is another vertex A2 and a color C2 such that A2 has infinitely many neighbors with color C2, right? So I can just continue this process over and over forever, right? I take these vertices that had an edge from A2 with color C2, I call them V2. Then again, I look at the induced subgraph on V2, and I continue this forever. So if I continue this process forever, I basically get 3 infinite sequences, right? I have the sequences of A vertices, of these colors that I had, the CIs, and also these infinite subsets of vertices. So I have V1, V2, so on, and all of these are infinite subsets. Okay, now again, I go back to my first point. I have finitely many colors, right? Because I have finitely many colors, there should be some color, I call it C prime, that appears in this infinite sequence infinitely many times. Again, this is just pigeonhole principle. So let's say that my color C prime appears at indices, let's call them I1, I2, etc. So these are are the indices where the color C prime appears. Okay. So what I do is that I just take the A vertices at these indices, at these indices. So I get AI1, AI2, and so on. And I call this V prime. So this is also the definition that I have written here. So V prime is the set of all those vertices AI whose corresponding color was C prime. Now again, by definition of C prime, V prime is an infinite set, right? And I also claim that all the edges between the vertices in V prime are of color C prime. Why? Well, because again, you can look at the construction. How was the construction done? V1 was a subset of neighbors of A1, and A1 had an edge of color C1 to every one of those, right? And this is also true for all other I, right? So if I get I1 and I2, AI1 had what? Had infinitely many neighbors of color CI1. And we call these VI1. And then I2 was inside VI1. So the color of the edge from I1 to I2 is definitely C prime. And you can say the same thing for any other two pairs of vertices. So this set V prime that I created is an infinite monochrome clique. So what you saw was just a very basic extension of this case. The extension was that instead of looking for triangles for cliques of size 3, we are looking for infinite cliques, infinite monochrome cliques. And also, instead of having just 6 vertices, we have infinitely many vertices. And as you saw, everything goes through. Okay. So now that we have this Ramsey theorem for infinite graphs, let's go back to our original problem, which was complementation of non-deterministic Bookie automata. Okay, so this is going to take a while. Let's say that I have a non-deterministic Bookie automaton A, my language, my alphabet is sigma, my set of states is Q, my set of initial states is Q0, my transition function is delta, and my target states or Bookie states are T. And I want to construct another non-deterministic Bookie automaton B that basically complements my original automaton. Okay. The first thing that I do is that I define some equivalence relation over finite words. Okay. And the equivalence relation that I want to define is basically, the intuition is this. When can I replace a finite word by another finite word? So let's say that I have an infinite word that is given as input to my automaton. And I want to see if I can just cut out some finite portion of it and replace it with some other finite word. And if I have this replacement property, and if I can do this without changing the acceptance, then I say that these two words are equivalent, and I show it like this. So I say V is equivalent to W. So let's make this formal. If I have two finite words, V and W, so these are in sigma plus. So they are finite, but they are non-empty. I say that V is equivalent to W if two conditions hold. The first condition is that for every two states of my automaton, if I can start from the first state Q and run V and get to Q prime, then I should basically be able to run W and also get to the same Q prime. Right? So this is the property that W should, it should be possible that we replace all occurrences of V with W. Right? And then the second thing is that this change should not also change any of the acceptance properties. So the second one is exactly like the first one, except that I say if I have two states Q and Q prime, and I have a run of my automaton from Q using the word V that gets to Q prime, but also visits the targets in between. Then I should have a similar run from Q to Q prime using the word W, and this run should also visit the targets. Okay, so the only difference between the second one and the first one was that here we're talking about runs that visit the targets. So what I'm basically saying is that if I have an infinite input to my automaton, and somewhere in this infinite input, I see the finite word V, I can just remove V and put W in its place, and nothing would change. Okay? So this is the equivalence relation that we defined. Now, how many equivalence classes do we have? Do you think we have finitely many equivalence classes or infinitely many? Yes, we have finitely many. And why? Well, because another way of looking at this equivalence relation is that we can consider a function that I call it f, that gets some state of my automaton and returns two sets of states. The first set is the set of states that can be reached using my word, using V, for example. And the second is the set of states that can be reached using V while also visiting a target. Right? So I can basically summarize the effect of a word V by a function that maps each state to two sets of states. And because the number of these functions is finite, then the number of equivalence classes that I have are also finite. And also, if I have such a function f, I basically show the equivalence class of f by LF. Now, here's the nice part. So what is an equivalence class? Well, we defined an equivalence relation over finite words, right? So an equivalence class, LF, is what? It's basically a set of finite words. So it's a finite language. So when we're talking about languages of finite words, one of the first questions that come to mind is this language regular? Can you have a non-deterministic finite automaton that accepts exactly this language? So let's say I take one of my equivalence classes that was summarized by this function f. And my question is this equivalence relation, is this equivalence class a regular language? Any ideas? Yes, it's basically, you can create a non-deterministic finite automaton for LF based on our original automaton for A. Yes. Yeah. So this is regular. Because you have a non-deterministic finite automaton that just accepts LF. And how can we create that? Well, we just take our original automaton and we take every pair, a given pair of states Q and Q prime, and we just enforce this. This can be enforced by a single automaton, by a single non-deterministic finite automaton. Then we create another non-deterministic finite automaton that enforces this one. And then we repeat this for every pairs of states, right? And then we just take the intersection of all of them. And because regular languages are closed under intersection, this is regular. Okay. So for each one of my equivalence classes, which I show by LF, there is a non-deterministic finite automaton that accepts exactly the words in that equivalence class. So LF is regular. Now, here's what I claim. I claim that if you have any infinite word, so any infinite word W that is in sigma omega, there is definitely two of these equivalence classes, which I call LF and LG, such that W is basically a word in LF followed by infinitely many words in LG. So what I'm saying is that I had these equivalence classes over my finite words, and now I'm claiming that any infinite word can be obtained by choosing two of these equivalent classes, LF and LG, and then taking one word from the first class and then infinitely many words from the next one and just appending them onto it. Okay, why? The answer is actually surprisingly based on the Ramsey theorem that we just saw. So here's how we prove this. So we know that there are finitely many different equivalence classes in our equivalence relation, right? This was because of this, because there are finitely many functions. So let's use each one of these equivalence classes as a color. And let's consider an infinite graph where the set of vertices is the set of natural numbers. And it's also a complete graph. So there is an edge between every two vertices. And let's say that I've colored every edge of this graph using one of my equivalence classes. So my equivalence classes are my colors. Okay? But how do I explicitly do that? The way that I do that is this. So let's say that my word W was this, W1, W2, these are each one character, one letter. So I define Wij as the substring from index I to index j minus 1. So it includes index I, but it doesn't include index j. Right? And then I have an edge from I to j in my graph. And I color that edge with the equivalence class of this string, of the substring from I to j, which doesn't include j. Okay? So this is how I color my edges in this infinite graph that I had. Now we can apply Ramsey's theory. Ramsey's theorem. Applying that theorem, we find out that there is some color, and remember that our colors were basically our equivalence classes, so I can call it LG, such that there are infinitely many indices that all the edges between these indices have this color, right? So this was Ramsey's theory, because Ramsey's theory said that there is an infinite clique such that all edges in this clique are from the same color. And this is exactly what I'm saying here, except that my color is LG. So I'm saying that there are infinitely many indices such that all the edges between these indices are colored with the same color LG. But by definition, the way that I colored was that I used the equivalence class of this substring, right? So this means that all these substrings are in the same equivalence class. So there are indices I0, I1, I2, so on, so such that the substring from I0 to I1, the one from I1 to I2, they are all in the same equivalence class LG. So, okay, let's just take the prefix from the beginning of our string to I0, and let's say that that one is in LF. Then my whole string is in LF, appended with infinitely many parts that are in LG. Right? So the part from the beginning of the string to the first index I0 is in some LF. And then from there onwards, because of this monochromatic clique that we had, all these chunks from I0 to I1, from I1 to I2, so on, these are all in LG. So I proved that every infinite word is basically of this form. It's a word in one equivalence class, followed by infinitely many words from a second equivalence class. Any questions until here? Okay. So we are running a little bit out of time, but I'm going to finish the proof. So you are welcome to leave, and you can then see the recording. Sorry about that, but I can't just let this slide for the next session because I have to go back to the beginning of this proof now. Okay, so here's another claim. I claim that if I take the strings that are of this form, basically the form that we saw before. So for some equivalence class LF and some other equivalence class LG, if I look at all the strings that are basically one string from LF followed by infinitely many strings from LG, then either all of them are accepted by my automaton or none of them are accepted by my automaton. So either the language of my automaton does not intersect this set at all, which means that all of them are rejected, or the language of my automaton contains this whole set, which means that all of them are accepted. Okay. How do I prove this? Well, let's say that I have some word W that is in this set. Okay. And let's say that it's also accepted by A. And let's say that I have another word W prime that is in this set, but I don't know if it's accepted by A or not. And I want to prove that W prime is also accepted by A. Now, I can decompose W in the exact same way that I did here. So I can decompose it into several parts. These parts are not letters now, they're again words. So I can decompose it into several parts such that W1 is from LF and all of the other parts are from LG. This is by definition, right? And I can decompose W prime in the exact same manner because W prime is also in the same set. Now, what do I know? I know that W1 and W prime 1 are both in the same equivalence class. So I can replace one of them by the other. And I know the same thing about W2 and W prime 2, W3 and W prime 3. So I can basically just replace each part. And this does not change the acceptance because of the way that our equivalence classes were defined. So basically, using this, I turn W into W prime without changing the acceptance of the automaton. So the automaton accepts W prime. Okay. So, yeah, and actually, I think I'm going to go over time for only 2 minutes. So here are the things that we proved. We proved that there are finitely many equivalence classes, LF. So there are finitely many classes of this form, right? Because if I have n classes of this form, I have n squared classes of this form. And we showed that every one of these LFs are regular. And we showed that every infinite word is in this format for some f and g. And also we showed that every set of this format either does not intersect the language of my automaton or is completely inside the language of my automaton. Okay, so now I want to complement my automaton. What do I do? Easy. I take my automaton. I have finitely many sets of this form. I check which ones are in my automaton, right? And now because I want the complement, I just take all sets of this form that are not in my automaton. And I create an automaton that accepts those. Now, how can I do that? I can create a non-deterministic Boole automaton that accepts this set, and then do it for each one of these sets and just take the union, right? So the only thing that I have to prove now is that there is a non-deterministic Boole automaton that accepts this set. And now I knew that LF and LG are both regular languages. So there is a non-deterministic finite automaton that accepts LF and a non-deterministic finite automatons that accepts LG. So I just put the automaton of LF, and from every accepting state, I put an edge to the beginning state of LG. Right? And then also in the automaton for LG, at every accepting state, I also put another edge back to the initial state so that we can have LG omega, we can see LG infinitely many times. So I can easily put the two NFAs for these two regular languages, LF and LG together, and just add some edges such that I get a non-deterministic Buki automaton that accepts this language. And then I do this for all the pairs that I need to do this for, and I just get their union. So this shows that omega regular languages are closed under complementation, because we could basically start with a non-deterministic Buki automaton A, and after doing all these weird things, we got to a non-deterministic Buki automaton B that accepts the complement of A. Okay, and this is it for this session. Are there any questions? Okay, so I'm going to stop the recording.